How do we graph rational functions with holes or slant asymptotes? Well, holes occur whenever you have a removable discontinuity. We've talked about that before. And slant asymptotes occur when the degree of the numerator is one more than the degree of the denominator. And then we got to do some steps after that. So let's just jump into it. All right, we're going to just find the x value where a hole will be for x squared minus 4 over x squared minus 2x minus 8. We're not going to go through graphing all of this just because the only step in this that you add is just putting a hole wherever the x value is. All right, so to find the hole, we first want to simplify it. And this rational function simplifies to x plus 2, x minus 2 over x minus 4, x plus 2. So here we have a removable discontinuity, so we have a hole at x equals negative 2. So whenever you would be graphing this, you would put a hole at negative 2. And just to show you, this is the actual graph of this function, and at negative 2, it's undefined. There's a hole. Sorry about this black dot at 0. All right, slant asymptotes. We should remember that if the degree of the numerator is larger than the denominator, then there's no horizontal asymptote. But sometimes they might have a linear slant asymptote. And that happens whenever the degree of the numerator is 1 degree larger than the degree of the denominator. And to find that slant asymptote, we're going to use polynomial long division. Whenever you're doing the long division, if there's a remainder, you can ignore it. Also, one thing to remember whenever you're doing the long division is that you have to put these zeros in any space that you don't have the term. All right, so just do what you've been doing for a long time and do the long division. And as you're working it out, you see, like, whatever this is just going to be my remainder. But in this case, I can ignore it because this 2x minus 2 is the equation of the slant asymptote. 2x minus 2, that's slope of 2, y-intercept of negative 2. All right, so let's see if we can put all this together and actually graph this function. All right, so we already found the slant asymptote was y equals 2x minus 2. And we don't see anything that cancels, so there are no holes. And we already said that there's no horizontal asymptote. It should be pretty easy to see right here that there are vertical asymptotes at x equals negative 4 and 3. And then remember to find the y-intercepts, set all the x's equal to 0. And the x-intercept, set the y equal to 0. All right, and setting all the x's equal to 0, we get that the y-intercept would be 0, 0. And if this is the y-intercept, then the origin is also the x-intercept. All right, now let's start graphing it. The first thing that you want to do is go ahead and plot out your x and y-intercepts, your asymptotes, and the slant asymptote. So here, I've already got the vertical asymptotes and my x-intercept. Now for the slant asymptote, I'm just going to graph the line 2x minus 2. And I'm just going to make it a dashed line. Okay, and this is an asymptote that is slanted. Okay, now once you have this slant asymptote, all you have to do is find some points on each interval, right, that's split up by the vertical asymptotes. And remember that in the middle, you can cross over horizontal asymptotes if need be. Now, for this example, it actually is quite off of this small graph that I have. So I'm actually just going to bring in a photo of what the actual graph looks like. So as you can see, like this graph would have been much larger than our 10 by 10, being that this point is already past negative 20. But here's what the slant asymptote looks like, and you can see, like here's my vertical asymptotes, and the slant asymptote stops the function on the other side, okay, and causes, just this slant. All right, and that's how we graph slant asymptotes. Goodbye.